So this is going to be intro to vectors. I will say in this video, we will only discuss two-dimensional vectors. So something with x, y coordinates, and we will not be discussing 3, 4, and upper dimensional vectors. Okay, so two-dimensional vectors only in this video, and it's going to be a very simple intro. So what we will discuss, we're going to solve, and this isn't necessarily in order, solve problems involving vectors. We're going to go over the definition of a vector. We're going to go over the anatomy of a vector because it has a couple different parts that we need to identify. We're going to be able to calculate its magnitude, which is a piece we'll talk about, how to draw a vector, how to add vectors together, and then solve vector problems if they involve bearing. So let's get going. So what is a vector? A vector is a quantity that has both magnitude and direction. And it's literally that simple. If it has magnitude and it has direction, it's a vector. Some examples are force, velocity, and acceleration. Let's look at some notation though, because you're like, well, how do I write vector? I don't want to just spell it out every time. So you can denote vectors with the capital letter of the vector. So whether your vector is V, A, whatever, we usually use a capital V though. Or you can represent a vector with your capital letter and this little arrow over the top. That's also known as a vector. Your tail and head, so see I have a little diagram of a vector here. Your tail point, your head point, and the little arrow, also a vector. And then we have these things called scalars. Now this is just a word to describe like just literal numbers. Like the number 5 is a scalar, right? It has what we call magnitude, but it doesn't necessarily have a direction. So think of, if you hear the word scalar, just think like, oh, this is a number, okay? And then the notation with the vector with the 2 vertical bars, that's what we mean by magnitude. That's how we say, hey, what we're talking about is the magnitude of this vector, not necessarily the vector itself, right? Because the vector itself has 2 components, direction and magnitude. But if we want to separate it and we want to just talk about the magnitude, then we use the vector with the vertical bars, okay? The anatomy of a vector, it has a tail, it has a head. It doesn't necessarily go on forever because it has a magnitude, right? It's a length. We denote vectors with arrows, where it has a starting point, the end point, and we have the arrow here because, right, we have to show direction. And the magnitude, you can think of magnitude as basically like the length of a vector. That's another way to think about it, even though that's not necessarily what it is. We want to call it magnitude, right? Because length is a really like two-dimensional thing, and vectors can exist in all dimensions. But I guess for us, since we're only discussing two-dimensional vectors, you can think of magnitude as length in the two-dimensional space. So how to calculate magnitude now? So on the xy plane, right, because I said in this video, we're only going to talk about two-dimensional vectors. This is not necessarily applicable. Actually, it's not applicable if you're going to do 3, 4, and upper dimension. But because we're just sticking in 2D, the magnitude of a vector, or vector with the vertical bars, is just the square root of x squared plus y squared. So for instance, if I have a vector that goes from the origin, here's my vector, right? We can see the direction. And I say that on the xy plane, this vector is ending at the point maybe 1, 2, right? Then for those of you guys, you know, this is similar to trigonometry. In trig, we would say, hey, that's r, right? That's the radius. It's r. R and the magnitude of the vector are going to be the same thing. So if we wanted to calculate the magnitude of this vector v, so we say, hey, here's my vector, then the magnitude of my vector v is equal to the square root of x squared plus y squared. So the magnitude of this vector, 1 squared is 1, 2 squared is 4, is going to be the square root of 5. And like I said, since we're only going to talk about two-dimensional vectors here, you can think about magnitude as length. So the magnitude of this vector is in fact square root of 5. Okay, So that's what we mean when we talk about magnitude. Think about length. Okay, and then this is derived from distance formula. Also, that's where that comes from. All right, the distance from here to the origin, x2 minus x1 plus y2 minus y1, the whole thing squared. So this is just literally distance formula. We're actually just literally finding the length of the vector. So now what if you're asked to draw a vector? And again, we're only going to talk about two-dimensional vectors in this video, mostly because you could not draw a four-dimensional one. So what if I wanted you to draw a vector? And right, we know a vector has direction and magnitude. 30 miles per hour due north. So remember north, east, south, west, or never eat soggy waffles. So if we want 30 miles per hour due north, so due north means literally only up, right? So our vector is starting at the origin. So here's our vector here. And the 30 miles per hour, that tells us the magnitude. So we have a vector that has magnitude equal to 30, and we're going due north. So if we were thinking about degrees, this would also be a 90-degree vector. Okay, so there's one. Now what about if I wanted you to go 50 centimeters per second, south, 50 degrees west? Okay, so south means I start from here and I'm going to go, so let me put my north, never eat soggy waffles. This 50 centimeters per second, south, 50 degrees west. So remember south, so we start on the south line, we go about 50 degrees. Let's see, 45 is halfway through, so 50 is just a little bit more. So starting at the origin. So here's my vector. And 50 centimeters per second, that means that vector has a magnitude of 50. And now this was telling me the magnitude, this is telling me the direction. Remember, vectors have two characteristics. You need to know the direction, and you need to know the magnitude, and there's your vector. So this vector, since I don't have any identifying quantity marks on here, I'm going to say, okay, well, that's length 50, and that is south 50 degrees west. So there's my direction, there's my magnitude. Okay, what if I say 25 miles on a course with bearing of 50 degrees? Now notice I didn't say south something west or north something east. If you don't see that with the bearing of 50 degrees, what we're going to do is we're going to assume that's from the horizontal axis here. So we're going to go here and we're going to open up 50 degrees, which is a little over halfway. So I've opened up 50 degrees. Here's my vector. And 25 miles, that tells me the magnitude. So this vector I drew in number 3 has a magnitude of 25, and it has a direction of 50 degrees, basically off the horizontal axis, so a bearing of 50 degrees. And then last, now what if I put this entirely notation and take out the words? So what does this mean? Remember the vector with the bars around it, so think absolute value is kind of an okay way to think about this because we're going to be used to be like, hey, those are the absolute value bars. Remember, absolute value bars also calculated distance. It calculated distance on the number line away from 0. The vertical bars in the vector is going to calculate the magnitude. Or in our case, since we're only talking about two-dimensional, it does calculate the distance of that vector. So it's okay to think about that as absolute value bars as well. So we have a vector with magnitude equal to 10 and theta 30 degrees, which means, so here's the origin, which means we're going to open counterclockwise 30 degrees, and 30 degrees is about here. It's less than halfway. So we opened 30 degrees. So that's what the theta gives us is, hey, how far are we opening? And the magnitude gives us, okay, that is going to be length 10. So vector needs to be length 10 or magnitude 10 and open up for the horizontal at 30 degrees. So now let's look at how to add these guys. So how to add vectors together, right? Vectors are really just arrows in space. And for us, they're going to be in the two-dimensional space. So what if I took two vectors and I wanted to add them together, which is a totally fine thing to do with vectors. Well, how do we do that? Well, if they're just like kind of floating off in space, we take them and we line them up head to tail. So if I want the vector u plus v, then u goes first, and see how this v in this diagram, we're like, okay, well, I'm going to slide v over there, and I'm going to make it line up head to tail. So if you line the vectors up head to tail, and then the vector u plus v is the big vector now that goes from the tail of u to the head of v. Okay, so I'll say that again. The addition of two vectors is the vector that's going to result after lining these guys up head to tail, and then you draw a vector from the head of the second guy to the tail of the first guy, and that's the vector. Okay, another way that you can do it is if you line them both up tail to tail, right? And then remember, these guys have directions, so these are naturally going to take off in the directions that they're going to take off. So you line up their tails together, and then you create a parallelogram, right? Be like, okay, well, if this is one half of a parallelogram, you complete the parallelogram, and then the vector that would go across the diagonal, that's going to be the vector of addition, okay? So that's what it looks like when you add vectors together. You can think about it as like, hey, we're combining them. The vector that results from the addition, though, is always looks like some kind of diagonal. Okay, so you can add vectors. So now let's look at a problem that involves vectors, right? Be like, okay, well, that's all great in an explanation, but like if I come across a problem, how do I use these guys to help me, right? Because ultimately everything is just a tool to help. So what if we had this problem? A bullet is fired into the air with an initial velocity of 1,000 feet per second at an angle of 35 degrees. So if I'm like, okay, I'm thinking of vectors, 1,000 feet per second, hey, there's a magnitude, and 35 degrees from the horizontal, there's a direction, and there's a magnitude. So let me draw my vector. So let's go, so direction and magnitude. So 35 degrees. So here's the bullet that's shooting off this way. Okay, so there's our vector. So now let's label it. So our magnitude is 1,000 feet. So again, we can think of magnitude like length in this instance because we're in the two-dimensional space. And our direction here is 35 degrees, which means there's a 35-degree angle between our horizontal and the path of this bullet. So now the question is, find the magnitudes. Again, we can think of this as length for this time period. Find the magnitudes of the horizontal and the vertical vector components of the velocity vector. So we have to kind of figure out, okay, well, what does that even mean? Well, if this is the end point here of our vector, then this would be the what we call the vertical component of the vector, and this would be the horizontal component of the vector here. And now you see that we have a perfect right triangle, which we're going to use to our advantage. Now, some labeling that you'll see, the vertical component of the vector, we call that vector y, okay, with a little subscript y, right, which makes sense because on our xy plane, y controls the height. So vertical component, v sub y. Horizontal component, v sub x, right, because x controls the horizontal movement. So when we talk about the horizontal component of the vector, right, what I have in red here, that's the vector. The horizontal component is, okay, well, from the tail to the head, how far horizontal did I go? Whether it's left or right, because it depends on the direction. Whereas the vertical component is, okay, from the tail to the head, how far up or down, because again, depends on the direction, how far up or down did I go? So think of this like way back when you were trying to figure out like points, like how to graph points, right? We'd go like over 3 and up 4. Well, that was the horizontal component and the vertical component. And what you guys were actually doing is vectors. We just didn't call it that then. So what we want to find is we want to find the horizontal and vertical vector components. We want to find the magnitudes of that, which basically is just asking, hey, what's the length of this blue line and what's the length of this blue line? which we have a right triangle, we have a degree, we know one side, so let's use some trigonometry. So to find v sub y, right, here's my angle. V sub y is opposite. 1,000 is the hypotenuse. So opposite and hypotenuse, so sine of 35, is going to equal opposite, which is our vertical component, over hypotenuse, which we know. Now, get rid of the 1,000, multiply both sides by 1,000. Those guys cancel out, and now we'll get our vertical component will be 1,000 times sine of 35, and this comes out to 1,000 times sine of 35. Make sure your calculator is in degree mode. We have 573. Did they tell us what to round to, or are we left to our own devices? No, but I'm going to guess whole number here, so 0.5, so that's actually going to round to 4. So 574, that's our horizontal, or sorry, our vertical component. 574, so we figured that out. Okay, now we need to find our horizontal component here. Now there's two ways we can go about this. We can use a trig function, or we can use Pythagorean theorem. What am I going to do here? Why don't I do something different? So we'll use Pythagorean theorem. So hypotenuse squared equals leg squared, which we know now, 574 squared, plus other leg squared, which is what we're going to try to figure out. So 1,000 squared is a lot of zeros. It's 1, 1, 2, 3, 4, 5, 6. 1, 2, 3, so we're just basically doubling the zeros. Equals 574 squared, and this is why I was a little hesitant to do it this way, because it's a lot of numbers. 3, 2, 9, 4, 7, 6. Oops, plus. All right, subtract these two guys, and we'll get our horizontal component squared is equal to 1, 2, 3 minus 670, 524. Now let's square root both sides, and let's see what we get. So square rooting both sides gives us 818.8, but let's round that up because we're going whole numbers, so I'm going to call that 819. 819. So there we go. We just figured out our vertical component as well as our horizontal component. We did this because we formed a right triangle, and then we used what we knew about solving for right triangles to figure these two things out. All right, let's do the last example. Okay, our last example has to do with bearing. So a ship travels 127 kilometers on a bearing of south 67 degrees east. How far east and how far south has it traveled? Now this is basically the exact same problem we just did, but instead of using words like vertical and horizontal, we're using directional words like south and east. So our ship travels 127 kilometers on a bearing of south. So this would be north, west, south would be down here, east would be over here. So here's south. So south 67 degrees east, which means I go to my south line, I'm go 67 degrees out, and I go in the east direction. So that puts me about here. So that's our ship. And we know that that is 67 degrees here, this angle formed right here. How far east and how far south has it traveled? So if we notice, east is our horizontal component of this vector. So how far east means basically, hey, how far left did we go? So I'm going to label this our v sub x again because that's our horizontal component. And then how far south? How far south did we go? and I'm going to label that v sub y. Oh, and we also know the length of our vector, right? We know our length is 127 kilometers. So we know this, but you're like, well, in the last triangle, I had this angle here. Well, we still do have that angle, right? If we know that this forms a perfect 90 and that's 67, then the remaining degrees, right? This is that angle's complement. So this would be 23 degrees. Okay, and now I have an angle in my triangle and I have a hypotenuse, and now I can figure out everything else that I want to figure out. So from this angle, I have, let's do again the vertical. So let's find v sub y. So from this angle, v sub y is opposite, and 127 is the hypotenuse. Let me draw on the right triangle here so you can see what I'm doing. So here's our angle, opposite and hypotenuse. So we're going to use sine again. The sine of 23, sine of our angle, equals opposite over hypotenuse. Multiply both sides by 127. These guys cancel. We'll get our v sub y, or in this case, our south, how far south we went, which is what we're solving for right now. So we just do 127 times sine 23. And we end up with 49.6, but I'm going to round that to a nice number. So 50. So v sub y, or how far south has it traveled? Well, it traveled 50, and look at, we're looking in kilometers. It traveled 50 kilometers south. And I figured that out because I found my vertical component of my vector. Okay, now let's find the horizontal component of the vector, because that's going to solve the problem, hey, how far east did we go? And last time I did Pythagorean theorem, so I'm going to switch it up. So here's my angle. I need to find my adjacent side, but I have my hypotenuse. So who deals with adjacents and hypotenuse? Cosine does. So cosine now of angle equals adjacent over hypotenuse. Okay, so again, I'm going to multiply both sides by 127 here, times 127. 127s are going to cancel out. And then my horizontal component of my vector is going to equal 127. Make sure your calculator's in degrees. Cosine 23. And we get 116.9. But I'm going for nice whole numbers. So what does that mean? That means that we traveled east 117 kilometers. Again, by finding the horizontal component of our vector, or our v sub x. So that's going to be the end of our video. So thank you guys for staying tuned. If you guys have any questions, like if you ever have any questions, please, please, please don't hesitate to ask. I know that was a lot, so you may need to watch a couple pieces over again. But ultimately, how you're going to learn this is starting to practice. So take the notes you compiled and go practice, and I'll see you next time.